Welcome, students, to our Chapter 2, Part 2 video lecture from our 2-semester General Chemistry series. This lecture will continue our cerebral hemorrhaging discussion on atoms, molecules, and ions. Many years ago, when I was working as a newly hired 15-year-old busboy at a small Italian restaurant in my hometown, my supervisor told me to clear all of the silverware, plates, drinks, and food from one of the tables near the back of our dining hall. "But there are still people eating there," I exclaimed. "They're done," he said. "Just go and clear their table." "Okay," I replied hesitantly, and I shuffled off to do as I was told. As mentioned, these people were still sitting at the table as I cleared it. In typical busboy fashion, I put one of my fingers in one of their drinks so that I could carry up to 5 glasses in one hand at a time. As I did so, one of the guests sitting at the table exclaimed, "You're putting your fingers in my drink." Now, he had a tone that to me at the time sort of sounded like he was just being sarcastic, and I thought he was just engaging in humorous banter. Besides, my supervisor had unequivocally told me that they were done and that this table needed to be cleared. Now, keeping in mind that I really thought this guy was just trying to engage in healthy and humorous banter with me, I replied cheerfully to him by saying, "Sir, here at our restaurant, we are happy to place any of our appendages in any of your beverages at any time." I then threw the drinks on my bus cart and left, taking these people's food and beverages back to the kitchen to be washed. I was soon informed by my supervisor's superior that these people were indeed not yet finished with their drinks. Unsurprisingly, I had to give them new ones. So just as I grew in my abilities as a teenage busboy with practice, so shall you grow in your skills as a young chemist if you give all due diligence to your studies. With that thought in mind, by the end of this lecture, you guys should be able to determine the number of electrons in an atom based on its charge, predict the charge of an element's most stable ion, explain what electronegativity is, and be familiar with electronegativity trends on the periodic table, and know the difference between ionic, covalent, and metallic bonds. But before I begin, I want to start first by sharing with you a humorous chemistry cat of the day from quickmeme.com. You should get this now that we've learned about neutrons, protons, and electrons from our previous lecture. Here it is. Neutron wants to pay a tab. The bartender says, "For you, no charge." Alright, so let's begin with today's pile of topics. First of all, sometimes we're asked to determine how many electrons a specific atom has. We can do that by solving the following formula. An atom's number of electrons equals its number of protons minus its charge. This brings us to one great problem from our problem set. There are blank protons, blank neutrons, and blank electrons in iodide 135. Now you'll notice by looking at this molecule, this is an I-. That means that it has a charge of -1. Now keeping in mind that the number of protons in an iodine is always equal to its atomic number, this iodine is of course going to have 53 protons because 53 happens to be iodine's atomic number. Now, given the fact that it has a charge of -1 and its number of protons is equal to 53, you ask yourself, how many electrons does it have? Well, we can use this equation. An atom's number of electrons equals its number of protons minus its charge. So if I take the number of protons, 53, and I minus a -1 from it, that's the same thing as taking 53 plus 1. So its number of electrons equals 54. Now, this hopefully will help solve some mysteries. You see, electrons have a -1 charge per electron, and protons have a +1 charge per proton. Thus, it makes sense that if you have an ion that is a charged atom that has a negative charge, it must have more electrons than it has protons. Conversely, if you have an atom that has a positive charge, it must have more protons than it has electrons. And here are some more problems that I think you can solve for your own. Which species has 54 electrons? And next, an ion, that is a charged atom, has 8 protons, 9 neutrons, and 10 electrons. The symbol for this ion is what? Now remember, of course, you can match that by looking at the number of protons. The number of protons will always equal that element's atomic number. I now wish to teach you about valence electrons. And what are valence electrons? Well, all elements, just so you know, have a certain number of total electrons, which is equal to their number of protons minus their charge. However, atoms' electrons are separated into 2 different types. their valence electrons and their core electrons. Valence electrons are the electrons found in the outermost layer of the element. If an element were an apple, then its valence electrons would be located on the apple's skin. Any other electrons in an atom which are located deeper down are called core electrons. Let's examine this more closely by looking at the periodic table. Take, for example, the element lithium, shown right here, which is located in group 1A. How many total electrons does a neutral lithium atom have? Well, it has 3, the same number as it has protons. But how many valence electrons does it have? Well, it only has 1, and the reason is because it's in column 1A. Hence, of its 3 electrons, only one of its electrons is a valence electron, and the other 2 are core electrons. Similarly, beryllium has 2 valence electrons, boron has 3 valence electrons, carbon has 4, nitrogen has 5, oxygen has 6, and fluorine has 7. Why? Because these elements are in groups 2A, 3A, 4A, 5A, 6A, and 7A respectively. Hence, the column number in which an element is found on the periodic table corresponds to its number of valence electrons, if the atom is uncharged. Now, what about elements in lower rows? Same thing. Every single element in column 7A, for example, has 7 valence electrons, spanning all the way down from fluorine to chlorine to bromine to iodine to astatine. In an analogous fashion, every single element in column 6A has 6 valence electrons, every one in 5A has 5 valence electrons, and so forth. Now, what about the elements in the D block? Well, for those elements, things are a little bit more complicated. I'm going to ignore them right now and just tell you this. For atoms in columns 1A through 8A, the column number is the same as that atom's number of valence electrons if you have a neutral, uncharged atom. Atoms regularly have the ability to gain or lose valence electrons. When this occurs, the atom's charge changes from being 0 to either being positive or negative, depending on whether you lose or gain electrons. But why would an atom ever want to lose or gain electrons? Well, generally speaking, all atoms want to feel like noble gases, that is, the elements that are found in column 8A. That is, they want to feel like they have 8 valence electrons. This is called the octet rule. Atoms do this by either gaining or losing electrons. When an atom gains electrons, it becomes negatively charged. When it loses electrons, it becomes positively charged. Each time an element gains 1 electron, it moves 1 column to the right on the periodic table in terms of how it feels. Each time an element loses 1 electron, it moves 1 column to the left on the periodic table in terms of how it feels. When elements gain electrons, they become negatively charged. When they lose electrons, they become positively charged. Atoms that have charges on them are called ions. So let's examine this by looking at our periodic table. If I were an oxygen atom, for instance, I would want to feel like the closest element on column 8A, which is neon. So how in the world can oxygen feel like neon? By gaining more electrons, either by sharing or stealing electrons from another element. If oxygen steals 1 electron from another element, it now feels like fluorine. Now, does it feel like neon yet? Nope. So what does it have to do? It has to steal a second electron. Now it feels like neon. Thus, oxygen is happiest when it gains 2 electrons, either by sharing or stealing them from another atom. Thus, oxygen wants to feel like it has a -2 charge, thus making it feel like neon. Once again, each time an element gains an electron, it moves 1 column to the right on the periodic table in terms of how it feels. Each time an element loses an electron, it moves 1 column to the left in terms of how it feels. When elements gain electrons, they become negatively charged, and when they lose electrons, they become positively charged. Atoms that have charges on them are once again called ions. By similar logic, fluorine would want to gain just 1 electron, feeling like an F- ion, which doesn't really sound like a very good grade at school, but is a wonderful grade if you're a fluorine atom. Chlorine, bromine, iodine, and astatine also similarly want to gain 1 electron so that they can each feel like the corresponding noble gases in column 8A that they are next to. Now what about elements way over here on the left side of the periodic table? What about lithium, for example? How could lithium feel like a noble gas? Well, we can imagine lithium gaining 7 electrons to become a lithium ion with a -7 charge and thereby feel like neon way in the world over here. But that might sound a little bit ridiculous, or at the very least, pretty challenging. I mean, gaining 7 electrons is a really tough journey for a lithium ion. Can it do something simpler to become a noble gas? Absolutely it can. You see, lithium could instead just lose 1 electron, its single valence electron. By doing this, instead of moving to the right, it moves to the left. And what is to the left of lithium? Well, if lithium loses 1 electron, it goes backward to feeling like the element that precedes it on the periodic table, which is the noble gas helium. By losing a single electron and moving 1 position to the left, the lithium now becomes a lithium plus ion. Now, similarly, sodium, potassium, rubidium, cesium, and francium would all just lose 1 electron each to also become +1 ions and thereby feel like the noble gases that precede them. So what about elements in column 2? You guessed it. Each of them is going to want to lose 2 electrons so that they can each move backward 2 positions to the left to feel like the noble gases that precede them. In doing so, they also become positively charged ions with charges of +2. Thus, elements on the left side of the periodic table tend to lose electrons, while atoms toward the right side of the periodic table tend to gain electrons in order to feel like noble gases. This fact is encapsulated very well by this table, which shows the most stable ions for the most common elements you will encounter. Hydrogen, which is shown over here, is interesting because it can exist either as an H- or an H+, depending on what it's bonded to. Which brings us to these beautiful problems, which I think you should be able to do on your own. First one says calcium forms an ion with a charge of what? The next one says barium forms an ion with a charge of what? We now broach a new topic, electronegativity. So what in the world is electronegativity? Well, simply put, electronegativity is an element's thirst for electrons. The more an element wants to steal electrons in order to feel like a noble gas, that is, to have a full octet, the more electronegative it is. Now, one thing that I demand of you, my students, is that you remember that electronegativity increases as you go to the right and up on the periodic table. Noble gases are excluded from this generalization. Why, you ask? Well, I'll explain that in a later chapter. For now, I just want you to remember this fact. Electronegativity increases as you go to the right and up on the periodic table. Thus, the most electronegative atom on the periodic table is fluorine, and the least electronegative element is francium. So let's see if you can do this lecture question. Identify the more electronegative atom in each of the following pairs. I feel pretty confident you can do this one on your own. Now, although I'm not going to show it to you, if you wish to see a table that gives numerical values of electronegativity for every element on the periodic table, you're welcome to click on this link. Now, as I've mentioned earlier, elements bond together so that they can share, donate, or accept, or give away electrons and thereby feel more like noble gases by completing each other's octets. This fact helps explain many of the ways in which elements behave chemically. Now, there are 3 different kinds of chemical bonds we'll now discuss. Ionic bonds, which are bonds between a metal and a nonmetal. Covalent bonds, which are bonds between 2 nonmetals. And now I have to specify that there are 2 different types of covalent bonds. Nonpolar covalent bonds, which we'll talk about later, and polar covalent bonds, which we'll also talk about later. The last are metallic bonds, which are bonds between 2 metals themselves. We'll also talk about these a little bit later. Now, by way of reminder from our last presentation, elements found on the right side of the periodic table are called nonmetals, which are shown in the blue section here. And they have very specific and similar properties to each other. Most elements found in this gray section over here are called metals and also have similar properties. And the elements who straddle the line between nonmetals and metals are called metalloids, which are highlighted in yellow here. Keeping this in mind helps us to answer the question, what are ionic bonds? To do so, though, we have to remember that nonmetals are much more electronegative, that is, thirsty for electrons, than metals are. So when a nonmetal bonds with a metal, the metal more or less completely gives its electrons to the nonmetal. By doing this, the metal becomes a cation, which is a positively charged atom, and the nonmetal becomes an anion, which is a negatively charged atom. This type of bond is called an ionic bond. So ionic bonds are bonds in which one atom has more or less completely negative charge while the other has a completely positive charge. The metal has donated its electrons to the nonmetal so that they can help each other feel like noble gases. For example, when sodium, Na, a metal, bonds with chlorine, a nonmetal, the sodium transfers one of its electrons completely to the chlorine, which forms an Na plus and a Cl minus, which is also known as sodium chloride, table salt, and is often abbreviated as NaCl. The Na plus is a cation and the Cl minus is an anion. Now here's a link to a great YouTube video showing this chemical reaction.
A small piece of sodium metal is placed in a flask containing yellow chlorine gas. The flask also contains sand to prevent the heat which will be generated by the reaction from cracking the glass. Initially, no reaction is observed between the sodium and the chlorine. The reaction will be initiated by adding a drop of water to the sodium.
This begs the question, why do nonmetals and metals bond with each other at all? And why is the formation of sodium chloride so energetic? Well, as this figure indicates, when chlorine gas molecules, which are each made up of two individual chlorine atoms bonded together, get together with a chunk of sodium metal, the sodium atoms each transfer their single valence electron to the chlorine atoms in a 1-to-1 ratio. This converts each sodium atom into an Na+, in which state the sodium now feels like the noble gas neon. And each chlorine atom becomes a Cl-, in which state the chlorine now feels like the noble gas argon. You now have NaCl, sodium chloride, also known as table salt. This reaction is so energetic because the process allows two very reactive elements to now each feel like very unreactive and stable noble gases. Now, parenthetically, I think it's interesting that sodium chloride, which is so stable and necessary for us to live, is made from sodium metal, which is explosive when it touches water, and chlorine gas, which will kill you if you breathe it. Now, if we were to zoom in on an individual chunk of sodium chloride, we would see an organized structure that looks kind of like this. As you can see, the chlorine minus ions, which are now called chlorides, shown in green here, are each surrounded in close quarters by their sodium plus counter ions, which are shown in yellow here. As we zoom out, of course, we see that this matrix or lattice structure is what makes up the white powder we know as sodium chloride. Now, one thing I hasten to mention is that positively charged ions, like our sodium pluses here, are called cations, and negatively charged ions, like our chlorides here, are called anions. I totally know, of course, I already mentioned this, but it's very important for you to remember. We should remember that these types of bonds are called ionic bonds. So that begs the next question. What are covalent bonds? Well, as mentioned earlier, when metals and nonmetals get together, the metal more or less completely transfers its valence electrons to the nonmetal. Both become ions in their journey toward feeling like a noble gas, and they thereby form an ionic bond. Now, by comparison, when two nonmetals bond to each other, they share their electrons, rather than one atom completely transferring its electrons to the other. This type of bond is called a covalent bond. Although nonmetals do share their electrons when they bond to each other, not all covalent bonds have a perfectly equal amount of sharing. When one atom is more electronegative than the other, the more electronegative atom will hog the electrons to itself a little more. Let's take a look at one example of a covalent bond by comparing sodium chloride, NaCl, with HCl. What's the difference? Well, unlike sodium, H is a nonmetal. Hence, hydrogen and chlorine form a covalent, not an ionic, bond. However, because chlorine is much more electronegative than hydrogen, the sharing of the electrons is quite uneven. This is illustrated in the following picture, which shows the much more electronegative chlorine atom mostly hogging the electrons to itself. This results in a partially negative charge on the chlorine and a partial positive charge on the hydrogen. Nevertheless, the formation of this molecule and sharing of each other's electrons allows each of these two atoms to feel like the noble gases that they're closest to. As you can see, no distinct ions are formed. Thus, this isn't an ionic bond in which a complete transfer of electrons has occurred. Instead, it's a covalent bond in which these guys are sharing electrons to help each other feel like noble gases. Nevertheless, because chlorine is more electronegative than hydrogen, it hogs the electrons to itself a little more, much like a monster truck would hog the rope in a tug-of-war with a Volkswagen Beetle. To summarize then, when a metal and a nonmetal bond, they form an ionic bond in which there's a more or less complete transfer of electrons. When two nonmetals bond, by comparison, they form a covalent bond in which they share electrons. The sharing of covalent bonds can be uneven if one atom is more electronegative than the other. And now I'd like to finish by sharing a funny story about HCl. You see, HCl is a chemical formula for hydrochloric acid, one of the strongest acids on Earth. Hydrochloric acid, interestingly enough, is not a solid or a liquid under regular conditions. It is a gas. One day back when I was in grad school, I had to run a chemical reaction that involved using HCl gas. This was done by connecting a valve to a small tank of HCl and running a tube from that valve into a reaction vessel I was running. Unfortunately, the valve apparatus we had in our lab was pretty old, and I wasn't sure if it would even work. This didn't stop me from trying, though. So sitting there with my HCl tank positioned in my fume hood and the valve apparatus connected, I opened the valve to allow the HCl gas to bubble into my reaction flask. As I feared, the valve did not form a tight seal in its connection with the HCl tank. Thus, gaseous HCl shot into my eyes. They were, of course, protected by safety goggles, but these were made mostly to stop liquids and did little to stop the gas from penetrating through their porous sides. The smell was very sharp, and it burned my nose and my eyes. I rubbed my eyes, and I noticed that my lab mates were also rubbing their eyes and noses, even from the opposite side of the room. "What is that?" one of them asked. "It's HCl," I replied. "My valve setup didn't work." "Hang on," I then said. "I'm going to tighten it really quick and try again." I did this in a few brief moments and then opened the valve again. Instantly, gaseous HCl shot once again into my eyes. "Ah!" I exclaimed, my eyes burning. My lab mates weren't very happy, as their eyes were also burning. "Okay," I said resolutely, still rubbing my eyes. "I'm going to tighten it one more time and try it again." I did this, opened the valve, and this time got shot once again in the eyes with HCl. "Ah!" I exclaimed. At this point, I decided to try giving up this reaction. So that's the end of today's lecture. Please tune in to my next and final video address, in which I will finish our coverage of atoms, molecules, and ions.